This was joint work together with Vera, Felix, Marc, and Emanuele from ISAC. And before I start, I would like to quickly give you some introductions about what is happening with hash-based signatures, because I think that's like quite different maybe when it comes to other PQC algorithms. So since 2018, actually, we have like the first kind of standard regarding stateful hash-based signatures. And that one is for extended Merkle signature scheme. Shortly thereafter, there was like the new RFC about Leiten-Micali signature schemes. And following these first two drafts or standards, authorities or regulations kind of stepped in and also gave recommendations about implementations, the usage, and how to build them. So we have one is the NIST Special Publication 2020. We have updated technical guidelines by the BSI. That's the German Federal Office for Information Security. And then we had also the ANSI that stated that you can use stateful hash-based signatures for your products, and you don't have to require on hybridation. So hybridation is that you run RSA or ECDSA in parallel to the lithium, for instance, which is required. And then something that happened last year, I think everyone is aware that Sphinx Plus was selected as a candidate in the PQC process. And something that has happened like in the end of the last year, which is maybe not known to research, or at least in the European Union, it's not so much aware, is like the statement of the NSA that they will update the so-called commercial national security algorithm suite. And with that, it will be enforced, for instance, if you have a national security system device in the United States that runs firmware signing or has to perform code signing, you have to use, starting from 2025 on, stateful hash-based signatures. And only these will be allowed, and you have to be in compliance with the NIST Special Publication 800, 208 on the page. So there we already see that you're kind of early, very early, have to run hash-based signatures. The second point I would like quickly to show you is like that it's not only that like authorities kind of push or are very advanced when it comes to hash-based signatures, but also we have companies already having available products. So the first thing I found, at least in the internet, was done by Cisco or announced by Cisco that they use LMS for code signing. Then we have from BlackBerry some notice that they offer a code signing service based on stateful hash-based signatures. And we have Genua that protects their software updates with extended Merkle signature scheme. And the last thing I was aware to find is from Infineon. They have a new TPM generation now available in the market, and they secure the firmware updates with extended Merkle signature schemes. So seeing this, that you have seen like we have already like products around in the market that you can even buy if you go to your local distributor, we thought about how does it look when it comes to implementation security. And there are like two topics to this. First one is side channel analysis. That one is actually quite nice when it comes to hash-based signatures. There was work done by Kanwischer, and he basically states in his work that DPA is promising, but fortunately we can simply, or it simply boils down to attacking the underlying cryptographic hash function. And that is something that is very nice because we can simply reuse research that has happened in the recent years and apply this to hash-based signatures with not much effort. Second thing is fault attacks. That's a bit different. There was, since or prior to our work, only like one paper presented by Castelnuovi et al., or one attack. It's the so-called grafting trees attack I will want to quickly introduce in the upcoming minutes. It's a very powerful attack, but has the drawback that it's not applicable to all hash-based signature schemes and not to all modes of operation. Since then, no other attacks are publicly known, and I hope that our paper somehow adds a bit to that. Before I want to go deeper, I would like to quickly introduce to you tree structures I will talk about. So when it comes to hash-based signatures, you always have like trees. The first one is like the single tree structure to the left that you see. And what you can simply see is like a Merkle tree, and then attached to the leaves, the so-called Winternitz one-time signature scheme. Taking the single tree, you can build multi-tree structures. And if you don't know like how this works, you could simply think of a certificate chain. So you have like the topmost tree. That one is your public key, that orange node. And then the topmost tree authenticates the middle one with this signature, this public key. And then the middle one authenticates the lower one, lower public key. And this actually then only signs your message. So you have like a multi-tree. Has some benefits when it comes to practice with signing, speed, and key generation. So these are the two tree structures. And if we go back to the grafting trees attack, think about that you would like to sign something. So what happens is that you run this full signing process. And here the lowest Winternet's one-time signature scheme signs your message. So assume that's like your first signing operation that you do. Then you want to sign another message. So what you have to do is, let's see where my laser is. There. So you used already that one-time signature scheme. So you have for the next message, skip to the next node in that leaf of the Merkle tree and use this one-time signature scheme. The attacker, what he does is during the signing operation, he introduces an error, shown here by the red little spark. Therefore, that node gets miscalculated. The topmost node, the root node, gets miscalculated. And then what happens is that you have reusing here the same one-time signature scheme, but for a wrongly calculated root node. And what simply happens is the reuse of a one-time signature scheme breaks security and is very bad. So this is very powerful, this attack, but has the drawback that you can only use it if you want to attack like a signer and only if there's like a multi-tree structure. So if you go for an embedded device, for instance, with running firmware verification, you cannot simply apply this attack. And also for stateful hash-based signatures, you have mostly single tree when it comes to practice. Getting back like to the tree structures, what I would like to show you is that we have Winternet's one-time signatures everywhere, and if we attack one of those, we could attack all the tree structures. And before I want to go deeper, it's a bit of a lecture because I didn't know like how many of you had knowledge or maybe have forgotten about Winternet signatures and how they work. First of all, what you could think of is like all these nodes. You could think of 128-bit values or 192-bit values or 256-bit values, depending on the security bit level you want to reach. First thing you do is you select your Winternet's parameter. In our example, it's simply 4. That defines the hash chain length of all the 4 hash chains we have in our example to 3. And if you run now a key generation, you roll your private keys, all these red nodes. Then you apply to each of the secret keys, you apply 3 times the F function. Think of the F function like a one-way function called to a cryptographic hash function. The result for all the 4 hash chains is then the final state. This you throw in the compressing function K, again, like called to a cryptographic hash function simply. And the result is then the compressed public key. That's the yellow node. This device, think of now, this goes into your embedded device, and with that you could verify like simply a single message. And if we now want to sign something, of course we have a message, we hash it, assume the hash length of the message is 1 byte. This thing we have to split into chunks. In our case, our chunks are 2-bit wide. That's defined by the Winternet's parameter. And now if you want to sign something, we simply apply the F function as many times as the value of each chunk. So it's quite simple. You do this for the first thing, so you result at the blue node. This goes into your signature. You do this for the second chunk, once F function for the third chunk, for the fourth chunk. And then you put all the blue nodes together. That's your signature. You take the message, send it to the device. What the device does is, again, hashing, splitting into chunks. And the device then simply finishes the hash chains. And so it does for the first chunk, apply once the F function to return at the final state, does this for all the 4 hash chains, and then apply the compressing function K. And the result is a candidate for the compressed public key. And if this matches with the internally stored compressed public key, you're good to go, signature is valid. So seeing this, and you probably have seen already Winternets, I think you know that that's weak and that's not how we use it, because what could an adversary do? It's shown with the green overlay. He could take a signature, select an evil message, hash it, and then hopes that his first chunks, for instance, has a 0 of 1 instead of a value of 0. He can take this blue node, which is public because it's part of the signature, apply once the F function, and now he has an evil tampered signature. And this will be verified as valid by the embedded device. So that's bad. What we do again in practice is like that we have a simple checksum mechanism in place. It works again very simple. It encodes the number of so-called steps left in all the hash chains. And if you do this for the simple example on the slides, you get a value of 6. This one you again split into chunks. You sign this by additional set of hash chains. And then if you want to run again this attack, it won't work anymore because your checksum value will be reduced to a value of 5. And what you can see is now, if you look at the last hash chain, is that the adversary actually has to inverse the F function, which is not feasible. Therefore, this node is unknown, and the attack no longer works. So this is more or less simplified how we use it. And now seeing that the checksum mechanism seems like very important, or is very important, we simply ask in our work, the question is, like, can we tamper with the checksum mechanism? How resilient is it? How easy is it if we tamper with it? And if we can tamper with it, is this already enough like to do forgery attacks against the hash-based signature schemes? To give you a bit of an idea what I mean with like tampering and faulting it, if you're like maybe not in hardware attacks, what could we do? We could, for instance, tamper the control flow. And to the right, you see like two simple scenarios that could happen. So the third line, you see, for instance, like the partial skip of a hash chain. So what could an adversary do? He takes the value of the node at index 3 for the last hash chain, puts it into his evil signature. The verifier wants to run these hash chain calculations. And as soon as the verifier is within the last hash chain running the calculations, the adversary injects a fault such that the first F function in that hash chain is not applied. We see that with the little cross. And so you have a partial skip of the calculations. Second scenario you could think of is like a complete skip. So the adversary takes the value at the node of index 4, so the endpoint, the final state, puts that into the signature. And then as soon as the verifier wants to again run the calculations, you inject magically a fault and such that there's no F function applied at all, and simply like a mem move from the states one to another. So if we assume something like that would work in practice and not only in theory, there's still one thing the adversary has to do, which I kind of ignored yet. And one thing is that an adversary chooses a message, then hashes it. And what we have seen before, we always have to land with the nodes to a value of equalness or greater than that of the original message chunks. So it's kind of shown with the green overlay to the right. And of course, we cannot select, or we don't know these values up front. So we need to do like a brute force search to fulfill these boundary conditions. And one drawback when it comes to this, like first of all, you have to evaluate a lot of different inputs. And one drawback when it comes to practice is that most of the times the message format you look at is quite limited, and your evil message is like kind of fixed, and you cannot really change it that many times. You don't have the possibility to introduce variants. What I want to quickly show you is like that for LMS and XMS, you can simply do that. You can keep the evil message constant if you vary the randomizer and the randomized hashing. And for Swings Plus, you could simply vary the authentication path, and this allows you to evaluate a lot of different input while you, again, keep the message constant. Maybe if that's interesting, the details are in the paper. So if I assume that, or beforehand I assumed that the theory, simply if we can say that this attack will work, we also evaluated this in practice to see if this is really an issue when it comes to the reference implementations that we have currently, and if you think about an embedded device. For this, we analyzed all 3 reference implementations of LMS, XMS, and Swings Plus that are public. We used Archie, that's a so-called architecture-independent emulation for fault injection that you can find on GitHub if you want to use it. We applied the fault model of a single instruction skip. Single instruction skip simply means that you have an instruction that is executed by your device, and by glitching or running electromagnetic fault injection, this instruction does not get executed, but for instance, a knob or the previously instruction gets re-executed. I have here on the slides for the talk only the results for XMS and only for the compiler optimization for size. The results for the other algorithms and the other compiler optimizations that we evaluated are very similar, and therefore it's just in the paper. So what we did is, first of all, we evaluated the case if we simply put an invalid signature into the system and we inject a fault, is that already enough to circumvent signature verification? What we can see for XMS at least, that it's quite resilient against a fault injection, and that's not working. Then the second scenario is like we evaluated our attack, where we either require to have a partial skip of the hash chains or full skips of the hash chains. And what we can see is, if we evaluated XMSS at least, that we have 8 distinct code locations in our binary where we could inject faults and therefore circumvent the signature verification. So this is of course bad that we can attack it, and so we as well thought about countermeasures, and we have 3 sets of countermeasures that we applied in our work. First one is what we can simply do is redundant computation of inexpensive operations. Something is, for instance, which is dangerous to be attacked, is the comparison of the public key and its candidate in the end, if you think about the yellow node in the graph before. The second thing, which comes to the hash chains more, is that when you think about this hash chain and the traversal going through it, what you can simply do is you harden this for loop and all the exit conditions such that you make sure the for loop is entered and it will not be exited prematurely. And the last thing that you simply need to do is, like regarding the partial skips, is that if you're in this for loop and going through this hash chain, you simply have to make sure that each of all of these f functions are called and that your adversary cannot simply skip this with a single injected fault. If we apply these countermeasures against to our attack, we can show that for all reference implementations and for all compiler optimizations, they effectively can hinder this attack that we proposed. And secondly, if you see that, I mean, it's quite nice that it's effective. Of course, you probably asked the point about price. It's an abandoned device. We have constrained resources. So we evaluated the increase of firmware code size, and we can see that the increase is roughly around 100 bytes. It depends a bit if it swings plus, LMS, or XMSS, and the compiler optimizations. And the nice thing is actually that, like for performance, you don't see a code size increase at all, because we designed the countermeasures such that we don't have to repeat any of the very expensive operations, like anything that's regarding hashing, and try to only make sure that it's really executed. Yeah, with that, I'm on my last slide. I hope I could show you that if we target WOTS, we can attack single tree and multi-tree structures. We can attack signing as well as verification. Something I didn't mention, but maybe is interesting for some of you, is that this allows you for either for an extensional or universal forgery. And I would like to end with, while this attack is feasible, I hope also it could show you that countermeasures are easy and efficient to be applied. And so you can harden your device if you fear about hardware attacks. Thank you.
How do you think both your attack models and your proposed countermeasures would differ in hardware implementations of these signatures for fault injection?
Yeah. So the fault models. So what we evaluated as well in the paper is like single bit faults. When you think about a laser, then you can like flip single bits. And if you think about, if you have accelerators regarding hash-based signatures, you have like these hash chains that you put into the hash chain accelerator. And there, of course, you have the same issue that single bits will introduce skips over this hash chain traversal. There, actually, it's, I don't know how you would like build a countermeasure to fix that, to be honest, right away. But yeah, you need to think about other countermeasures to kind of make sure, like harden your state machines probably, then also harden your buses, have code error correction for the buses. Yeah, probably you needed a different set again of countermeasures and depending on the accelerator. Yeah, gets again tricky.
But the attack models will be essentially the same.
Yeah, so it will still work. I mean, I'd like last year we had like built an accelerator and put out, and for that one I'm 100% sure that everything will work that we presented here. Like it was not built with countermeasures in mind, and that you could easily skip and you could apply the same attack to it. Don't know for other accelerators so far. Yeah. Thanks.
So I have one question. In your talk, you mentioned some stateful hash-based signature scheme. How do you feel about like companies? Do you think that they could handle that in real life? Because you have to take care of the state, otherwise reuse would obviously leak the signature. And yeah, so how do you feel about that?
Yeah, so one thing is like that, at least for me as a researcher, was quite interesting that the NSA announced that they will only allow XMS and LMS. I mean, I don't know about national security systems, but it seems like they only allow stateless. And state management is quite painful, at least for most of the companies, I guess, I talked to. For me, I think that like big companies, I mean like Cisco, Infineon, they probably know, or I hope they know how they do that securely, and that they can like really keep the state safe over redundant locations. I think the best thing is like if you think about secure boot and firmware signing is to go for a hybrid approach, so that you have like the semiconductor company that goes for stateless to have a very flexible and fast thing. And then I think like if you think about an application developer, I wouldn't trust them that they can run like the state management securely up to 10, 20, 30 years. And they should maybe go for Sphinx Plus better and pay the price in performance. Yeah.
And, oh, sorry.
No,
and just to add to this question, so do you think that it's, I mean, it's possible to imagine that a company doing stuff seriously could do the key management, but do you think that it's still possible to share the key between a lot of devices or user or something like that? Like, would the key management be, I mean, it's going to be harder, but do you think that it's still manageable in this case?
You mean the distributed state? Yeah. Yeah, there's, like when you look at the NIST special publication, they proposed like to use a multi-tree distributed state management. And with that, I think you quite easily can share around like a distinct set of keys to other locations. That works quite nicely. For me, I think it would be nice to have a solution that requires only a single tree and not a multi-tree, because if you think about multi-trees, you duplicate your signature size, you duplicate verification cost. And if you have a single size tree, in compliance with the NIST special publication, so this allows you to export or share key material. But I think, in my opinion, you could do something with subtrees and so that you don't have to export keys and don't make it public, so that you don't have the issue, but simply align it in a single tree. That would be nice, I think, for to make it more performant. But I think, as far as I know, there's not yet a work about it out there that makes it possible. Yeah.
Great. Thank you very much. So let's thank the speaker again.